The ocean sediments actually harbor one of the largest sources of methane on the global planet. And so they're trying to understand whether there is any connection between the ocean sediment methane and the Earth's atmosphere and climate is one of the sort of underpinnings of a lot of the research that we're doing here. We're trying to capture many different aspects of the fate of methane that resides in the seafloor. Currently we are in the Astoria Canyon off the coast of Astoria, Oregon, diving on some sites of bubble emissions from the seafloor. The ones we're currently diving on are about 850 meters in depth.
These locations are interesting because they're very, very microbially rich, and that's why there's methane seeps at all. And the reasons that they're microbially rich are related to the metal content. So something like this site in Astoria Canyon receives a tremendous input from the Columbia River. And the Columbia River is the primary source of metals to the ocean, and it's also a primary source of organic matter.
We're looking at things like how is methane released from the seafloor in the form of bubbles, what form does it take, how fast does it rise, how fast does it dissolve into the water column, how much actually gets transported upward in the water column, how much methane in the sediments is being consumed and oxidized into carbon dioxide or bicarbonate. So we're really trying to get that more holistic look and capture of what's going on. The interdisciplinary nature of what we're doing right now is we are bringing physicists, chemists, engineers, and microbiologists all together in the context of one cruise. We've brought a number of different really interesting instruments, forms of cutting-edge technology that are being used that we're really excited about. We have on board an in situ mass spectrometer that's used to analyze gas concentrations. So in general, the idea of a mass spectrometer being underwater is a bad idea. It's going to be a hard thing to do. It's going to be a difficult thing to operate. Another instrument that has been developed more recently is a laser spectrometer, and this allows us, through what's called absorption spectroscopy, to differentiate between the different isotopes of methane, the C12 and the C13 isotope of methane, in the methane sample as we're underwater. So are there any challenges to working with these types of technologies underwater? Anytime you're trying to put some complicated electronic or optical or vacuum system underwater in the ocean is a harsh environment, it's a harsh place, and it doesn't cooperate all the time. Often the element of surprise, the elements of the ocean, the deep sea, can get involved and make things not work. Too often, oceanographic research is limited by the collection of samples, then 6 months later you're analyzing samples back in the laboratory and saying, oh boy, it really would have been really nice if we could have done something more at that site. It was really interesting. Well, 6 years from now we'll go back. What we're trying to do is bring the chemistry laboratory to the seafloor so that we can make informed decisions about the conditions that we're sampling at that time, see that feedback in real time.